Hello, this is your test review for Unit 1, and we are going to use this graph for the first few questions. So these are all just finding the limits. So letter A, limit as x goes to negative infinity. So the left side of the graph is going downwards, so that would be negative infinity. Limit as x goes to positive infinity, this side of the graph is leveling off at 0, so we are headed towards 0. All right, here we're going to -1 from the negative side, so from the left. So here's -1 as we approach from the left, we are approaching 3, approaching -1 from the positive side, so -1 from the right, we are approaching 1. And then limit as x approaches -1 overall would be does not exist. And that's because of the jump discontinuity. The left side goes to 3 and the right side goes to 1. So if we zoom in on that point, it's not coming to the same place. All right, limit as x goes to 4 would be 1. Limit as x goes to 3 from the left. So here's 3 from the left-hand side, we're going downwards, so negative infinity. And limit as x goes to 3 overall would be does not exist because there's an asymptote there. So you can only do one-sided limits if there's an asymptote. Otherwise, it would be does not exist. Now, these are actual functional values. So is there actually a point there? So f of 4. Now, the limit was at 1. Both sides are approaching 1, but that actual point is at -2. F of -1. So the actual filled in point is right here at 3. F of 3, there's an asymptote there, so there is not a point, so it does not exist. And then here we're talking about continuity. So at 0, our function is continuous. There are no breaks or jumps there, so that one is yes. At 3, we have an asymptote, so that's no. Now you have to use correct notation. There's not a point at 3. So we're going to say f of 3 does not exist for our explanation. And you have to make sure you use this correct notation. All right, at 4, there is a point and there is a limit. They just don't agree with each other. So no, the point at 4 doesn't equal the limit as x approaches 4 of the function. So there is a point and there is a limit, but they don't equal each other. The limit is at 1 and the actual point is at -2. All right, and then x equals -1. Again, no, there's a jump discontinuity. So we're going to say the limit as x goes to -1 of this function does not exist. So there is a point, but there's not a limit. Both sides, the left and the right, aren't coming to the same. All right, so we're done using that graph. Number 4, if a function is continuous at a point -1, 5, what are 2 things this tells us? So in order for continuity to happen, you have to have a point, you have to have a limit, and they have to equal each other. So we know we have this point, f of -1 equals 5. That's the first thing we know. And then we know that the limit as x approaches -1 of the function is going to equal 5. So those are the 2 things that we have there. There's a point and there's a limit, and they're both 5. So f of -1 is 5, and the limit as we go to -1 of the function is also 5. All right, for this function, we want it to be continuous at 2. So what would the value of, oh, sorry, typo, that should be a +2. I'll fix it for your copy. The value of f of 2 must be what? So essentially it's a limit question. We're going to do the limit as x approaches 2 of this function. And so if you plug in 2, you're going to get 0 over 0. And so we're going to multiply by the conjugate to cancel this out. So square root of x plus 7 plus 3. And so I'm going to bring this limit notation with me. When we multiply this together, the roots are going to cancel, which is, the whole idea. We'll have x plus 7, and then -3 times +3 will be -9. For the denominator, you don't want to do anything with this. Just copy both of these factors over, just leave them alone. Because if you try to multiply all that out, you're just going to get a big old mess. All right, and then x plus 7 minus 9, that is x minus 2, so these cancel, which is the whole idea. You want to get something to cancel. Once you get that to cancel, you can go ahead and plug in the value you're approaching. Now this numerator is going to be 1 since everything canceled out. And if we plug in 2 down here, we'll have square root of 9, which is 3, and then 3 plus 3 gives you 6. So 1/6. All right, and then we have a whole bunch of limits analytically, which means we don't have a picture to look at. Here we're approaching 4 from the right. So we're going to try to plug in 4. 4 plus 1 gives you 5. 4 minus 4 is 0. When you get a value over 0, that means you have an asymptote. So you're just going to check if their graph is going upwards or downwards. If it's not sided, you would automatically know that it does not exist, but this one's from the right. All right, so the numerator's 5. 5 is positive. And we're going to test a number bigger than 4, something to the right of 4. So like 5. 5 minus 4 would be 1, which is positive. So we get a positive over a positive, and we know the graph is going up. So positive infinity. All right, this one, if you plug in -4, you're going to get 0 over 0. So we're going to have to do some algebra until we can get something to cancel out. Because I have this fraction within a fraction here, I'm going to try and get a common denominator. I'm going to put that 2 over 1. We're sort of just looking at the top part of this. And the common denominator would be x. So I'm going to multiply those by x and put all this together. So that would be 8 plus 2x over my common denominator of x. And then that is all over x plus 4. And so I want something to cancel, and I'm going to do that by factoring. So we're going to factor a 2 out of this. If you factor out a 2, you're going to be left with 4 plus x, which is the same as x plus 4. So those are going to cancel out. And so again, once you get something to cancel, then you can just plug in the value that you're approaching. So we're left with 2 over x. If we plug in -4, we'll have 2 over -4. So -2/4, which would reduce to -1/2. All right, and then these next few are going to positive or negative infinity. Those are your horizontal asymptotes. You want to compare the highest powers. Kind of like who's in charge here. So for the numerator, that's the 3x squared. For the denominator, it's the -x squared. It's a tie, so we're going to use the coefficients. It would be 3 over -1, which would be -3. For this one, the numerator, we have that -x to the first. Denominator is the 2x squared. So this is really a 1 here. The numerator power is smaller than the denominator, so it is automatically going to be 0. And then here we have the 4x to the 5th, and then the -10x cubed. So the numerator power is bigger. That means it's either positive infinity or negative infinity. You just need to check if it's going upwards or downwards. So this is x goes to positive infinity. You want to imagine plugging in an enormous positive number. So if you take a big positive number to the 5th, it would still be positive. Multiply it by 4, it would still be positive. If you take a really big positive number to the 3rd, it would still be positive, but then we're going to multiply it by a -10. So that denominator would be negative. And so this is going downwards, so negative infinity. All right, here, if you think about plugging in a really enormous number, we're then going to make it negative. So when you have a negative exponent, that reciprocates. And so instead of being really, really important part of this function, it ends up being very, very unimportant. Like we've flipped the negative exponent. So that portion is going to go to 0. And so we're just left with a 1/2. And to compare and contrast, number 12 is the same thing, except without the negative in there. If you think about plugging in a really enormous number, this e to the x is going to get huge. It's going to be really, really, really huge. So you're going to have 1 over an absolutely enormous number. So like 1 trillionth. Which is super, super tiny, and it's going to go to 0. And if you're like, hey, but what about the negative? It just means it's going towards 0 from the underneath side, like from the negative side. All right, here, if we think about plugging in 3 minus 2 gives you 1. So this would be ln of 1, which is 0. I basically just threw this on here to remind you that ln of 1 is 0. This is your graph of ln. You have that asymptote and then the point 1, 0. So just on here as a reminder of that. All right, and then we have some trig. So for this one, we're going to factor the denominator. And that means we can take out an x. We'll be left with x minus 2. So this sine of x over x part goes to 1. So essentially, you can sort of ignore that. That's going to go to 1. And then you can plug 0 into what's left. So you're going to have 0 minus 2, negative 2, with 1 in the numerator. So negative 1/2. And then here we're going to need to factor. This is a trinomial in the numerator. Just instead of, like, think of it as 2 minus x squared. It's just instead of a plain old x, it's a cosine of x. But it's the same concept. We're just going to factor that apart. So the 2 is going to split 2 and 1. The cosine squared is going to split cosine and cosine. And to get a negative 1 cosine in the middle, we would need these outsides to give us negative 2 and the insides to give us positive 1. And this 1 minus cosine of x over x, that part goes to 0. So it really doesn't matter whatever else is here. If that part goes to 0, 0 times anything is going to be 0. So those are the two properties that you need to know. That sine of x over x, that goes to 1. And the 1 minus cosine of x over x goes to 0. All right, and then we have the piecewise function. So we're going to approach 2 from the left, 2 from the right, and then 2 overall. So from the left means we're going to use this portion, x less than or equal to 2. If you plug in 2, you're going to have 4 minus 4, which is 0. The common mistake here is people will plug in a number smaller than 2, like they'll plug in 1. You want to plug in that actual number. The left or right just tells you which piece of the function you're using. So we're still going to plug in 2. From the right means we're going to use this piece. So if you plug in 2, 2/4 would be 1/2. And then 1/2 minus 3 would be negative 2.5 or negative 5/2. And then overall would be does not exist. If these don't match up from the left and the right, that means you're going to have a jump discontinuity. One side is going one place and one side is going the other. Now, if these were equal, like say this was 0 and this was 0, then this answer would also be 0. They would all be the same. All right, number 17. Is the function continuous at -1? So do these pieces match up at -1? This is a little tricky because if you plug in -1 here, you get -1. And if you plug in -1 here, you get -1. But because there's not an equal to on either of these, there would be a hole there. So that's no. But if one of these had the equal to on it, then it would be a yes, because when you plug in the -1 to each of those, they do meet up. All right, then is the function continuous at 5? Well, if you plug in 5 here, you get 5. And then here is just 7. So if one side goes to 5 and one side goes to 7, again, you're going to have a jump. They don't meet up, so no. All right, 18, find the average rate of change. That just means slope of this function on the interval -2 to 1. So we need a point for -2 and a point for 1. We're just going to plug those in. So if you plug in -2, you're going to have 4 minus 8, which would be -4, minus 7 would be -11. And if you plug in 1, you're going to have 1 plus 4 would be 5, minus 7 would be -2. And then you just do the slope. So subtract your y values, it would be -2 minus -11, so plus 11. And then 1 minus -2, so plus 2. And you can simplify that if you want to, but if it's not multiple choice, you don't have to. You can just stop there and leave it alone. All right, for number 19, we're given values in a table. Estimate the derivative at 2.7. So we can't find a derivative exactly because we don't have a function. To estimate it, we're going to do a slope. So 2.7 would be, somewhere in between here. And so these are the 2 points that we're going to use. So subtract your y values. It'll be -3.4 minus -1.7. And then subtract your x values, 2.8 minus 2.6. And again, you do not have to simplify that down. I recommend not worrying about it because if you make a mistake, it's going to be wrong. And also for time purposes, you don't want to take your time doing that if you don't have to. All right, here, find the derivative using the definition of a derivative. So that's limit as h goes to 0, and then we're going to plug x plus h into the function. And then you subtract the function itself. And then that is all over h. And then you're going to do a whole big lot of algebra. It's not hard, it's just a lot of distributing. So this x plus h squared, that's going to multiply out to be this. And then you have to distribute a 3 into that. So it's going to be 3x squared plus 6xh plus 3h squared. So that's this first part. Then we're going to distribute the -8. And then we've got this -2, and then we're going to distribute this negative. So again, these are all of your algebra skills here. And this is all over h. So the good news is everything without an h in it should cancel out. And if you don't get that to happen, it means you just made a mistake with your algebra somewhere. You probably missed the negative sign. The 3x squareds are going to cancel. The 2's are going to cancel. And the 8x's are going to cancel. So these 3 terms are left. We're going to factor an h out of them. And that would leave us with 6x plus 3h minus 8. And then the h's cancel. And we can go ahead and plug in 0 for h. So if you plug in 0 for h, this term's going to be gone. You just are left with 6x minus 8. And so that is our derivative, is 6x minus 8. So write the equation of the tangent line to f of x at x equals -2. So to write an equation, you need a point and you need a slope. And the x value, our point of tangency where we're writing this, is at -2. So to get the point, you're going to plug -2 into the original function. So let's see, -2 squared would be 4 times 3 would be 12. -8 times -2 would be 16. And then -2. So 12 and 16, that would be 28, minus 2 would be 26. So you just plug your value back into the original function. For the slope, you're going to use this derivative that you got. So we're going to plug -2 in for x for the derivative. So that would be -12 minus 8, that would be -20. So that's our point and our slope. And we're going to use point slope form. So y minus 26 equals our slope -20, and then x minus -2, so +2. And I'm fine with you stopping there. If you want to add over this 26 so that the y is by itself, you can do that too. But I'm fine with you stopping there. All right, here we're going to use this table for the next 2 questions. Average rate of change just means slope. So we want the points. For 2 and 4, you just have to make sure you read the table correctly. So function g, so we're going to be looking at this column. 2 gives us 3, and then 4 gives us 2. And then we're just going to do the slope. And again, I'm fine with you stopping there. You don't have to simplify it. If you accidentally subtract wrong, it's going to be wrong. So I would just leave it. Our equation of a tangent line, you need a point and a slope. And our point of tangency is 2. Now this is for function f, so just make sure you use the correct part of the table. So f of 2 is 4, and then slope comes from the derivative, that's f prime. F prime of 2 is -1. And then we're just going to put it together into the equation. It'll be y minus 4 equals -1, x minus 2. And again, if you want to add that 4 over, you can, or you can just stop there. All right, so we're not using that table anymore. That was just for these 2. So 23, a differentiable function has the property f of 3 equals 9. So that means we have the point 3, 9. And f prime of 3, so that's our slope, is 3/5. We're going to estimate 3.1 using the local linear approximation. That means the tangent line at 3. So we're going to use this point and slope to write the equation. Y minus 9 equals 3/5 x minus 3. And the reason we can estimate 3.1 is that it's really close to the point of tangency. You have to pick something that's pretty close to 3. The further away from the point of tangency you get, the less accurate your estimation is going to be. So all you have to do is plug in 3.1 and get y by itself. So I'm just going to add over this 9. And I put the swirly equal sign because it's an estimation. So it'll be 3/5 times 3.1 minus 3. And then again, I'm just adding that 9 over so that the y is by itself. All Right, use the alternative definition of a derivative. So we're going to find the derivative at a specific point. So not limit as h goes to 0. This just gave us a general formula for the derivative. For this one, we want to find the derivative at a specific point. So we're kind of bypassing this and just going straight to the answer at a specific point. So we want this at x equals -3. So limit as x goes to -3. And then it's the function. So 3x squared minus 4 minus whatever you get when you plug in the point that you're trying to find the derivative at. So we're going to plug -3 into this function. So -3 squared would be 9 times 3 is 27 minus 4 is 23. So it's the function minus whatever you get when you plug in your value, and then over x minus -3. So x plus 3. Now this is going to be indeterminate. You're going to get 0 over 0. So we need to get something to cancel. If you were to combine these together, you would have 3x squared minus 27. And we can factor a 3 out of that. So if you factor 3 out of x squared minus 27, that would leave you with x squared minus 9. And then that is a difference of squares. So it's going to split x plus 3, x minus 3. And then the x plus 3s are going to cancel. Again, once you get something to cancel, you can just plug in the value you're approaching. So -3 minus 3 would be -6 times 3 would be -18. And so that's the derivative at that specific point. All right, 25. There are several reasons a function would not be differentiable. List each and draw a sketch showing each. So the first reason your function would not be differentiable is if it's discontinuous. And so all your different discontinuities, you can have a hole, you can have a jump discontinuity, or you can have an asymptote. And sometimes if you have a hole, the point would be somewhere else. But if your function's discontinuous, then it's not going to be differentiable either. If you have a sharp edge, which would be a corner, like an absolute value, or a cusp, which looks kind of like a bird flying. And then also if you have a vertical tangent line. And the reason for that is it would look something like this, where your graph goes vertical right in the middle. Because, by definition, the slope of a vertical line is undefined. So like by definition, it would be undefined there. Since a vertical line slope is undefined. All right, we're looking at this piecewise function. Is the function continuous at 1? Now that just means the two pieces meet up. So we're going to plug 1 into both pieces of the function and see if they come out to the same thing. So I just plug in 1 here, plug in 1 here. This is going to give us 3. This is also going to give us 3. So is the function continuous there? Yes. And this is your work that you're showing. Is the function differentiable at 1? Now we have to do the derivative from each side. So this is the same formula that we did for number 24. We're just going to have to do this from the left and the right. We're going to do the derivative at a specific point, which in this case is 1, from the left and from the right. So from the left, we're going to use this piece of the function. So it is the 3x squared minus whatever you get when you plug in 1, which we just did right here, is 3 over x minus 1. And it's going to be indeterminate. We're going to have to get something to cancel. If you factor a 3 out of this, you would be left with x squared minus 1, which is a difference of squares. It'll split x plus 1, x minus 1. And so the x minus 1s are going to cancel. Once you get it to cancel, you can just plug in your value, which is 1. So 1 plus 1 is 2. 2 times 3 is 6. So the derivative or the slope from the left is 6. And then we're going to do the same thing from the right. So that means we're using this piece of the function. So it's going to be the function itself, 6x minus 3, minus whatever you get when you plug in 1, which again, we just did it right here, is 3. And then over x minus 1. So in the numerator, This would be 6x minus 6. And if you factor a 6 out of that, you're going to be left with x minus 1. So again, this was 6x minus 6. Minus 3 and minus 3 would give you minus 6. If you factor a 6 out, you'd have x minus 1. So those cancel and you get 6. So the derivatives from the left and the right are the same. So the function is differentiable, which is actually kind of strange. That doesn't happen too often. But in this case, it did. We did the derivative from the left, derivative from the right. They both came out to 6. So yes, the function is continuous and differentiable. All right, for 27 and 28, we're going to use this graph. On what intervals is the slope of the tangent, that means the derivative, positive and negative? All right, so positive is where the graph is increasing, negative is where the graph is decreasing. So positive would be this portion, so -2 to 0. Negative would be these portions where the graph is decreasing. So that would be everywhere else, -infinity to -2, and then 0 to infinity. So positive derivative, that's where the graph is increasing, negative decreasing. And then what are the critical values? That's where you have these 0 slopes. So that's at -2 and 0. And then here we're going to sketch some derivatives. So the first thing you want to put on here are the critical values. This one has a critical value at 0. Our graph is increasing and then decreasing. So we want to be positive and then negative, which means above the x-axis and then below. So we want to be above the x-axis and then below and go through that point at 0. Also, this is quadratic, so the derivative of that should be linear. You go down a degree. So if you look at this one's cubic, so its derivative should be quadratic. We should get a parabola. Your critical points are at -2 and 4. And this graph is increasing, decreasing, increasing. So we want to be positive, negative, positive. So we want to be above the x-axis and then below and then above. So we did end up with a parabola. And then this one, absolute value, you have a slope of -1 for this portion. And then a slope of +1 for this portion. So you're going to have a horizontal line here at -1 up until this sharp edge, which is happening at 2. Now there'll be an open circle there because the graph is not differentiable at 2 because of the sharp edge. So we're going to have a slope of -1 up until that corner point at 2. And then after that,